All right, we're going to continue our discussion about reactions and talk about physical and chemical changes. We talked about some of those earlier, different types of chemical reactions. So we're going to talk about a little bit more about acid-base today and precipitation reactions, which are net ionic equations. And just to get started here, when we talk about chemical and physical changes, it's important for you to distinguish between a physical change where only the states change and there's no new substances formed in a chemical change. Now, in a chemical change, there can be state changes. We can create new states of matter, but we're doing that by creating something new. Like when you change oxygen and hydrogen into water or back into the gases. There is a state change there, but we're forming new things. So you have to look and see if you form new substances. If you form new substances, then automatically that is a chemical change. If there's only an interruption of those IMFs, then that's a state change, and just simply a state change, that is a physical change. So you need to understand the difference between rearranging ionic and covalent bonds around, which would be a chemical change, versus just interrupting those IMFs. So the changes in forces and bonds when water boils. When water boils, we are simply just changing, we're reducing or eliminating the intermolecular forces between the water molecules, as opposed to when we take electricity and go through electrolysis and we split that water molecule into its hydrogen gas and its oxygen gas. That is a chemical change. And you are breaking covalent bonds in order to do that, as opposed to here where you're breaking intermolecular bonds. Some changes, such as salt going into water, are more difficult to characterize. So in the past, when I talked to you about water and salt coming together, I would always say that that's a physical change. Well, there's a little gray area there, because we're actually breaking intra bonds when we're talking about the sodium and the chlorine, and intermolecular attractions are broken between the solvent water molecules. So this part right here, the intermolecular attractions being broken, that is a physical change. But when we're talking about these intramolecular bonds here, where you've got between the two, the sodium and the chlorine, that's actually a chemical change. And so this gets into that kind of a muddy gray area. I always taught you in regular chem that this was really just a physical change because we could get that salt back pretty easily. But now we need to think of it in terms of, okay, we're actually breaking some of these ionic bonds. And in doing so, that's technically a chemical change. Depends on who you talk to about this. If you talk to a more advanced chemistry type person, they're going to say that this is a chemical change. If you talk to someone who is less experienced with it, they're going to argue with you that it's a physical change. So just kind of be ready for that. AP considers it a chemical change. So you've moved up into that mastery kind of level where you're expected to be able to identify that. All right, acid base. We did spend a little bit of time last year in chemistry on this. If it wouldn't, I would have liked to have spent a lot more time, but we got through as much as we could get through. So we're going to identify an acid base. When we do this, our definition of an acid is that it's going to donate hydrogen ions, and a base is going to accept those hydrogen ions. So if we look at the two sides of the equation, we're going to find the two things that are similar to one another. Whichever item between those two things that has more hydrogen, that is our acid. So this is going to be our acid. This will be our conjugate base. Over here, these two things belong together. This one has more hydrogen in it, so this is our conjugate acid, and this is our base. Down here, these two things, you can see similarities between them. So this is our conjugate acid. This is going to be our base. Between this and this one has more hydrogen. So this is our acid, and this will be our conjugate base. This side is considered conjugate, and this is non-conjugate, I guess, was how you would phrase it. All right, you need to have these memorized. These are your strong acids, and they are going to completely ionize in solution. No original compound will remain. We'll talk about this more when we get into acid-base equilibrium in Unit 8. But for right now, you need to set about getting all of these memorized. Okay, it's an easy thing to do for the bases because if you look at your periodic table, you have your lithium, you have your sodium, you have your potassium, you have your calcium, you have rubidium's down here. We don't really memorize that one though, because they're never going to use that one. Calcium followed by your strontium. Strontium right underneath calcium. Yep. Strontium and your barium. So you really need to have these memorized and these memorized. And they're all hydroxides. And if you look at your periodic table, you can kind of see that it forms a pattern here. And so it's easy for you to be able to find those on the periodic table and just remember, oh, yep, that's where it kicks over. K, it kicks over to Ca and we go down. And then we just add hydroxide to those. These you're just going to have to memorize. Okay. A lot of them are your Brinkelhoffs, so that helps a little bit. But, you know, some of it's just going to have to be memorization. Now, when it comes to sulfuric acid, it's the first proton that is a strong acid. So what will happen is it'll release a hydrogen ion, and then it'll leave you with that as your formula. Okay, so this hydrogen is the one that is a strong acid. This one will end up being a weak acid. And like I said, we're going to talk more about strong and weak acids when we get into Unit 8 and acid-base equilibrium. All right, so strong acids will completely disassociate. They're going to give off that hydrogen ion. Weak acids only partially disassociate. So about 5% ionize and the rest will stay as the original form. So if you were to think of this as like a teeter-totter, essentially, when you got done with your reaction, your teeter-totter here would be sitting at this point where you have very little HCl left and everything's formed out into these ions. If we look down here with a weak acid, if we had a teeter-totter, it's going to go the other direction. So we'll have very few of these. We'll have a little bit of them formed, but most of the stuff will stay in the weak acid section. Okay, strong bases, same idea. 100% disassociation with these. Weak bases, very little. Neutralization reactions, then we can put an acid and a base together, and what they're going to do is they're going to create a salt, and they're going to create water. Okay, strong acid, strong base, you'll end up with a pH that's 7. Strong acid, weak base is going to be a pH that's less than 7, and a strong base and a weak acid will be a pH greater than 7. When strong acids and bases react with a when strong acids react with a strong base, this is the equation that you essentially end up with where you're going to be forming water. Okay, weak acids, strong bases here. Your potassium will cancel out. You're going to leave your acetate ion here, and water will be formed as well. Gas forming reactions then, we had some of these on your sheets that I gave you last year in class, the bright orange sheets. You have, for example, calcium carbonate. You've got hydrochloric acid here. They're going to form carbon dioxide gas and water. Same goes down here for your sodium bicarbonate and hydrobromic acid. And then we talked about H2S last year as well.